In this video, we are going to do some examples with uniform distribution. I strongly recommend you watch the previous videos in my series on uniform distribution. They will explain a lot about the formulas and the processes that I'm going to be using for these examples, where here I kind of go quickly because I have three parts. I've got an easy example, a medium difficulty level example, and a challenging difficulty level example. And for the challenging one, I'm going to do it two different ways, just in case you have your own way of doing probabilities in your classroom or yourself personally. Okay, so I have chosen a story problem I've made up because I'm waiting for the tram at my favorite zoo, Binder Park Zoo in Battle Creek, Michigan. It's distributed uniformly between 0 and 15 minutes inclusively. I got that problem because when I go to the Binder Park Zoo, they have a tram that takes you to another one of the cool exhibits there, and it says on a big sign, tram shows up every 15 minutes. So that means you're either getting on the tram when you get there, or you're jumping on 15 minutes later. That's if there are, no other people in line taking up the space more than one tram length. So we are going to write and define the probability density function and the area map I have set out for you. So let's write the probability density function. First of all, f of x, which is saying the function, is equal to. Now, it looks like I have to go between 0 and 15 minutes, so maybe doing a little bit of work on my area map will help me create my function. So I know I need to go between 0 and 15 minutes. And the height of this function has to be 1/15. And the reason why the height has to be 1/15 is because this entire rectangle is 15 units wide. Let's see if I can draw a straight line here. Okay, now, I think sometimes people get confused as to why this denominator is the same as this length over here. Well, if you have the area of any rectangle, it's either length times width, or you can call it length times height. So to find this area, we would take the length of this rectangle, which is from 0 to 15, which is 15, and then we would take the width of this rectangle, which also you could call a height here, and the height is going to be 1/15. If you multiply fractions, top times top, bottom times bottom, and this bottom is 15 over 1, you get 15 over 15, top times top, bottom times bottom, and 15/15 is 1. So the area of this rectangle is 1, or 100% of the possibilities probabilities. So that's why the the denominator of that fraction and this length is the same. So always use the height here equal to the width of your rectangle. All right, and we'll see this again and again as we do these problems. So the function of x is 1/15, or that height, when x is between 0 and 15 seconds. And we would write it this way. 0 is less than x, which is less than 15, which again is a cool way of saying x is between 0 and 15 inclusively, okay? And inclusively could also mean less than, you could have equal to symbols under here. I'm not going to get too far into the weeds about that because you could technically weight 0 or could technically weight exactly 15, but we're just going to leave it like this, thanks to how the book would do this work. So let's look at the theoretical probability that the person will wait less than 12.5 minutes. Okay, so 12.5 minutes, I'd say it's about here, okay? So that's about 12.5. And what I'm going to do is I'm going to highlight everything to the left of the 12.5. Okay, so everything to the left of the 12.5 is highlighted. So what percent chance do you have of landing in the yellow zone? Well, it looks like you have better than 50% because it's, more than 50% is highlighted here. But let's find the actual answer, okay? So the actual theoretical probability would be taking your width and dividing it by the overall width of your area model, and that is going to give you 0.833. Now, your XYZ homework may want this in 2, 3, or 4 decimals. Be sure to round correctly because this is 0.83 repeating, And I like doing 3 decimals because we can easily see this is 83.3%. And it's closer to 83 than 84. That's why I like to go one more decimal beyond just a normal percent. Okay, so let's do the theoretical average and the standard deviation of waiting in line. Okay, so the theoretical average. That formula is pretty straightforward because the theoretical average is your min plus max. You could also say max plus min or high plus low of the rectangle's width or distance or x-axis or domain is another way you could say it. And you divide it by 2. So this is finding the midpoint. The balancing, just as a reminder that averages are balancing points. So if you say to yourself, if this whole thing was filled, so if this whole thing was yellow, not just the side to the left, if this whole thing was filled up, the balancing point, you could put your finger right in the middle and that tray would not tip in either direction. Well, the average is 0 plus 15 divided by 2, which is 7.5. So 7.5 minutes is the average. So they could say on that sign, you know, instead of saying the tram comes every 15 minutes, it could say the tram has an average of 7.5 minutes. But let's do the standard deviation, which is a little bit more complicated of a formula. First of all, inside the square root, you've got the high number of your x-axis minus your low number of your x-axis. That touches your rectangle, squared, divided by 12. Okay, so now we just have to kind of use order of operations to do this correctly. Inside the parentheses, we have 15 minus 0, so we'll do that first, and then we will square it, divide it by 12. Then we lastly take the square root. Kind of working inside out here, 15 squared is 275, and we're going to divide that by 12 before we take the square root. So this is 18.75. Then we take the square root, which gives us 4.33 minutes. So the 7.5 is the average. Give or take, because that's what the standard deviation is telling us, give or take 4.3 minutes for normally speaking. So, you know, 68% of the time, this tram will be between, let's see, if I subtract 4.3 from 7.5, around 3.2 minutes. And again, 68% of the time, it's going to be between the 3.2 and the, let's see, add the 7.5 and the 4.3. So that would be 11.8. So 68% of the time, we're going to be, you know, 3 to 12 minutes. You know, that's just rounding to make things easier. That would be a very complicated sign just to write down, like, hey, the average is 7.5, give or take 4 minutes, and, you know, make the people learn some math while they're waiting. So let's now do the last part of this easy level problem by finding the 90th percentile. Now, finding the 90th percentile for waiting in line is really, we're looking for some x, right? This is x is how long you're going to wait. And then how long you're going to wait times the height of your rectangle is going to give you 90%. Now, I don't know where 90% is. I'm only going to guess that it's somewhere around that squiggly black line right there. Because if I shaded in all of this over here, this would represent about 90% if all of this right here. So this is about the 90th percentile. So 90% of this rectangle is filled in. Now, to find that out, I'm just going to have to do some algebra. So x times 1/15, to solve for x, we have to get the 1/15 to the other side. So let's do the opposite of multiplying by 1/15. And some of you might say, well, the opposite of multiplying is dividing. Dividing by 1/15 is a bit weird. So what I'd like to do is maybe instead of dividing by the 15th, I'm going to multiply both sides by positive 15 in the numerator. And what that gives me is this gives me on the left-hand side 15 divided by 15, which is 1 times x, which is just x. Now, some of you would call that canceling. I like to call it simplification. Now, I've got 90% times 15, so 90 times 0.15 gives me, typing that into a calculator, 13.5, and 13.5 minutes is my answer. And so you can see that 13.5 is my waiting time if you're the 90th percentile. Only 10% of those who basically, you would, I can't say 10% just because it doesn't guarantee that everybody's showing up at every available time. You would be higher than the 90th percentile if you waited between 13.5 and 15 minutes. So that is the end of the first problem. The easy level problem. Let's level this up a little bit by shifting your time frame. Okay, so now what we have is we have a tram at Binder Park Zoo, and it's basically going to now be between 10 and 25 minutes to get, to pick you up, basically. So the wait and loading time of the tram is 10 to 25 minutes. Now, here's the thing. I thought of this problem because, yeah, that tram is going to come every 15 minutes, but it's going to take 10 minutes to load. So now instead of us basically getting going between 0 and 15 minutes, now we're getting going between 10 and 25 minutes. 25 minutes being basically you waiting the full 15 for the tram and loading, and the 10 minutes is just, kind of getting there and loading. So let's take a look at the area map and how this changes the probability density function. So 0 is basically the least amount of time you can wait for the tram, but then you've got 10 minutes for the tram to basically for you to load onto it. And between that 10 and the 25-minute mark are the possibilities of you basically waiting to get on your way. So this time, the 10 and 25 includes waiting for the tram and loading. So here's where, and I can tell you from previous semesters, I can tell you where things get a little precarious, because what happens is that people put the wrong numerator and denominator here for this fraction. First of all, the numerator is 1. There's not too many people who get that wrong, but the denominator is not 25. The denominator is still 15. Now that confuses people because in the previous example you said, well, hey, Mr. Anderson, it looked like the highest number was my denominator. And that was true because your rectangle was shifted all the way to the left-hand side of your y-axis here. But it's not in this case. See, in this case, the rectangle shifted to the right 10 units, going from 10 to 15. So the difference between 10 and 15 is, 10 and 25 is 15. So again, we have another situation where the area is equal to the length, which is 15, times the width, or the height, which is 115. So my area is equal to 1, which we always need to have. If our area is not equal to 1, we don't have this uniform distribution area map done well. So now my function is still 1/15th, but notice how it's different. It's different from the function above it because we're not going between 0 and 15. We're going between 10 and 25. So 10 is less than x, which is less than 25, which is a fancy way of saying x is between 10 and 25 minutes. So in the previous problem, we took a look at the theoretical probability that a person will wait less than 12.5 minutes. Well, here we have the same thing, except what we have to do is we have to look at the difference between that 12.5 and the 10. See, notice how small the 12.5 and the 10 is. Let's use a little highlighter to show you that. So if someone's getting on the road to that other exhibit in Binder Park Zoo in 12.5 minutes, this is a very small part of our entire rectangle, so it doesn't look like this is very likely. So we're going to have to take our 12.5 and subtract our 10, and we're going to divide that by 15, which is the height of our triangle right here, or height of the rectangle right here. I could also have written this out like this, 12.5 minus 10, which is our x, times 1 over 15. This is, again, equivalent to this before it. So this and this are the same thing, and this gives me 2.5 divided by 15. I see a lot of students skipping this step here that I'm circling in gray and just going to this step right here, this 2.5 divided by 15. That's cool. That's cool because you've kind of leveled up and thought about the problem and got to your answer of 0.1666666666666. But let's round it to 3 decimals, so this gives us about 16.7%. This is not very likely to be hitting the road and checking out that other cool exhibit at Binder Park in 12.5 minutes. So let's find the theoretical average and standard deviation of this problem. As we discussed before, the theoretical average is the balancing point here. So it's halfway between 10 and 25, which we can use as a median problem. So to find the median, just like you did on all of those frequency polygons back in the last unit, you just do your low number and your high number divided by 2. So that is going to be 35 divided by 2, which is 17.5. So there's my theoretical average of how long is it going to take you to get the tram to you and load the tram. 17.5 minutes. Okay, 17.5 minutes. Now let's do the standard deviation. Okay, standard deviation, it's high minus low of the rectangle, quantity squared divided by 12, then we take the square root. So we got 15 squared divided by 12, then we take the square root. 225 divided by 12, then we take the square root. And wait, 225 divided by 12? Or, excuse me, 200 and... I think I screwed up on the previous problem. Sorry that I said it was... Did I say 275? I think I meant 225. Oh, let's fix that. Instead of 275, that is 225. You can stop your furious emails here. I caught the mistake. But 225 divided by 12 then gives me the same standard deviation as before of 4.33. Now you might say to yourself, hey, how come the standard deviation was the same between this problem and the one before it? Well, it's the same rectangle, it's just shifted over to the right a little bit. So the same rectangle will have the same standard deviation because you didn't change the size of the rectangle. So again, 17.5 minutes, give or take 4 minutes, is going to be roughly 68% of the time you're going to be between those two spots. And the 90th percentile for waiting in line, let's see, that is going to be, in this case, a little trickier this time, because now instead of just x times 115 gives me 0.90, now we have to say x minus 10. Now, I find very few students are going to solve it this way. Let me show you an alternate reality way that people solve this problem without putting the x minus 10 in parentheses. They would go x times 1/15 equals 0.90, and then multiply both sides by 15, just like we did in the previous problem. That simplifies x is equal to, in this case, x is equal to 13.5. Now, if you're kind of paying attention to this problem and the one before it, you'll notice that, wait a second, that 13.5 was literally for the previous problem where we didn't wait 10 minutes. So now I'm going to have to add that 10 minutes back in the problem. So my x is equal to 23.5. It's cool to see how many people find the answer this way by getting the 13.5 and going, wait a second, that doesn't make any sense for being in the 90th percentile, because the 90th percentile has to be way over here on this side of the shape, and 13.5 is like right here. It's just to the left of the 12.5. That doesn't look like 90% of the area. So I've had some students figure that out later by basically looking at that answer and asking themselves, that doesn't, does that make sense? That doesn't make any sense. Now, if I go to this problem over here, the one with all the fancy algebra, I would multiply 15 on both sides, and the 15 simplify here, and I get x minus 10 is equal to 90 times 0.15. Sorry, 0.90 times 15 is 13.5. I looked at my answer first. 13.5. And then to get the x by itself, we'd have to add 10 to both sides, which gets us to our 23.5. And you can see now why this is a medium level difficulty problem. The big mistake, again, people make a huge mistake with this height. And unfortunately, the height, if that's wrong, you're probably going to get problems 6, 7, and 8 wrong, thanks to the wrong height. So be very careful with that. So at this maybe halfway or 2/3 way of the video here before we get to the challenging example, maybe you should pause it, take a break, get yourself a glass of water, hydrate a little bit, get up and stretch, check that phone to see if any important messages came in, because when you want to pause this video, we're going to do a very challenging problem 2 different ways. Okay, so here is the challenging problem, because I'm throwing in conditional probability into this uniform distribution problem. So it says, suppose the wait and loading time for the tram at Binder Park Zoo is between 10 and 25 minutes. Okay, so we kind of understand that. Find the theoretical probability that you will wait more than 20 minutes, having already waited 15 minutes. Okay, so what happens is that your friend is already at the other part of the exhibit. And they're going like, hey, where are you at? And you're like, I'm waiting for the tram. I've already waited 15 minutes. So hopefully I don't have to wait much more. So what we have to do is we have to look at the area map made on the previous problem, the second one. And what's a little challenging about this, if you screwed up that picture, then this one's going to be wrong too, because what you have to have is you have to have the height of 1/15th, and you have to go between 10 and 25. So if you had this picture wrong on the previous page, then there's no way you can get this one right. So the notation for this is the probability, the notation for this is the probability of UX, almost wrote a different letter there, URX, you waited more than 20, having already waited 15. Okay, so here's the conditional probability notation. What is the chances that you waited more than 20, having already waited more than 15? Okay, so now what we need to do is we need to kind of imagine that this rectangle is a stick of butter. Okay, because what has happened so far is that you have already waited 15 minutes. So this portion of the butter left of the 15 is going to get cut off. And what's left here is this part, which is between 15 and 25, and we just want to see what is the chance of you landing in that 20-minute or more zone up to the 25. Well, what's cool about this is that you can kind of see, you can kind of see from the conditional area map is going to make this a lot easier, because as I said, this spot between the 10 and the 15 is going to be gone, because we are not going to consider it, because you have waited that moment up to 15, okay? And the highest possible moment you could wait is minute 25, and we just want to know the chances between the 20 and the 25. So your height is no longer 1/15th, it's 1/10, because the space between the 15 and the 25 is now 10. Because our area, again, of our length times width has to be equal to 1. So if the length is 10, that width or height can be 1/10. So now we have a different height of our area map. And it says in the next problem here, we're going to now use this conditional area map. We're going to basically take our high minus low of the region that we want to find. We want to see what is the chance of me landing in this yellow zone. Now, a few of you out there watching this video are like, oh, I can see what the answer is. You don't need to show me all the work. I can tell you that it's this percent. Okay. I understand you can see that, but I'd like to still do the answer here, because this is going to be our high possibility minus our low possibility of that rectangle part right there, multiplied by the height. See, this is our length and our width. Here's our length and our width, which is also height if you want to. So we've got 25 minus 20 times 1/10, which is 25 minus 20 is 5 divided by 10, and 5 divided by 10th is 1/2, or 0.5, or 50%, and really doesn't that look like 50%? And it does, it does. There is a 50% chance of that tram coming between the 20 and the 25-minute mark, and there's a 50% chance that that bus is going to, or tram is going to come between the 15 and the 20-minute mark. So that was using the notation in the area map method and the rectangle. But what I want to show you is I want to show you the conditional probability method here using the notation of the probability of x is greater than 20 and x is greater than 15. So this is a nod back to my probability unit, where we can actually use the full size of our area map going back to when it started at 10. And by the way, I'm cheating this a little bit just so I have more room to write here. So this is going to be 15, and this is going to be 20, and this is going to be 25. Okay, I'm really off on my scale here. So I'm going to, like, just because my brain can't stand it, let's just do some uniform tick marks here. 20, 15, and 10. Now I feel like this is too wide, but you know, you get the idea. All right, so now I have these uniform pieces here. The height of this model between 10 and 25 is 1/15, okay? So this is my numerator. My numerator is going to be the probability of this and this, where my denominator is the probability of this. Because according to the definition of conditional probability, we have the probability of A and B happening divided by the probability of B happening. So let's just kind of write that out. A choose B divided by the probability of B. Okay, so at this moment you may have checked out already because the previous answer made a lot more sense, but this is for my probability heads that want to use the definition of conditional probability, so I'd like to show this here. So my numerator is the probability of x being greater than 20 and x being greater than 15. Well, if you have to be greater than or equal to 20 and greater than or equal to 15, you're going to be in this zone right here, which is 5 units out of 15 units, because the width here is 5 and the height here is 1/15. So that's how I got my 5/15. So this is my numerator, and I'm going to put that down here as 5/15. Again, you're copying this down. This is probably not the way you're going to solve this, but again, I like to show people this method because some people want to use the definition of conditional probability. Okay, so this is 10, this is 15, this is 20, and this is 25. Okay, so now what we have is we have x is greater than 15. Okay, so that would be this yellow spot right here. Now that is going to make a numerator of 10 and a denominator of, well, I changed that to blue. I really want to, yeah, I do want to keep that blue. I'm sorry, I did the thing I was thinking of. Okay, now the reason why this is 10 is because the distance here is 10 and my height here is 1/15, or 1/15, I could put that there. So that is now my denominator fraction. Okay, so 5/15 divided by 10/15. And we're going to use a little college algebra to solve this complex fraction, because we got a fraction divided by a fraction. And as I always say, dividing fractions, please don't cry. Just skip the first fraction, flip the second fraction, and multiply. So if we do this problem like this, and of course those of you with calculators could probably have done this as well, you could have multiplied top times top, bottom times bottom. You could also do some cross simplification or cross canceling, you might have heard. And that gives me 5 in the numerator, 10 in the denominator, which is reducible to 1/2, which is 50%, which some of you can have seen, because if you look at this chunk versus these two chunks, the two chunks size-wise make basically half in the numerator than it is in the denominator. Whew, okay, you've been through the most challenging problems you can possibly deal with. I would say that your test could encompass the medium and easy level difficulties, but I'd like to push you a little bit in the notes and the homework so the test doesn't feel like a challenge. So thank you for sticking through these 3 easy, medium, and difficult examples of continuous probability.